Hello everyone, welcome to my YouTube channel. My name is Evidence, and in today's video I am going to show you how to build principal component analysis using Scikit-learn. And in the next video I'll show you how to explain your principal component analysis using a script plot. And then in the next video I'll show you how to build principal component analysis manually. So this is gonna be a 3-video series. Make sure you subscribe to the channel to get all 3 of them. With that being said, let me go ahead and give you a small preview of PCA. If you already know what PCA means, you can skip this part of the video. So principal component analysis, or PCA, is a dimensionality reduction technique that transforms a high-dimensional dataset into a new lower-dimensional dataset while preserving the maximum amount of information from the original data. So if you had a dataset with 100 columns, after you do PCA, you might end up with like only 4 PCs in like 4 features. So it does reduce your dimension from a lot to very small, and it does that while retaining the maximum amount of important information from the original data. And whenever we are dealing with principal component analysis, we encounter something called eigenvector and eigenvalue. So what exactly is eigenvector and eigenvalue? Eigenvector is a vector that doesn't change its direction during a transformation. So an eigenvector can be scaled up, which is stretching it, or scaled down, which is squeeze, but the vector doesn't change its direction. So the value that scales the eigenvector up or down is called the eigenvalue, and both of them come in pairs. With principal component analysis, we are extracting the most important features from our dataset by creating another new set of features that captures the most important information from the original dataset. So basically, this is another way to word what I said right here. PC is our principal component, which is what we gain from doing PCA, captures a combination of the features with the highest variance with a little sprinkle from other features. But majority of the information in PC is from the features that produce the highest variance during a linear combination. So PCs does not have 100% of the information in the original dataset. Rather, each PC explains a certain percentage of the original dataset. The goal of a PC is to select PCs that account for greater than 90% of the variance in the original dataset. Now, when I show you how to explain your PCs using a script plot, then you will see how to find PCs that has the highest variance. So the pros of a PCA is that it will reduce your dimensions, the dimensions of your features. But there are 2 main cons to doing PCA. First, we don't know which features to combine to create a PCA. So we don't know what features in our original dataset combined to create PCA 1. We don't know what combined to create PCA 2, stuff like that. And also we are trading off predictive power / ability to reduce dimension, because not all features in the original dataset are captured in principal components. Like I said, your goal is to select PCs that represent greater than 90% of the variance in the original dataset. So we are trading off predictive power for reduced dimensions. So with this brief overview on PCAs, let me go ahead and show you how to do your PCA using Scikit-learn library. There is a process to this. You can go ahead and look at this or copy it or whatever. Whenever you're doing PCA, you want to follow this process. First, you want to get your data ready for analysis. Then you want to standardize your data by subtracting the mean of each column from each value and dividing each column by a standard deviation. So your mean is gonna be 0 and your standard deviation will be 1. This is, if you're doing this manually, this is how you do it. But if you're going to be using a library like I'm about to show you, then you don't need to do this manually, but you still need to standardize your data. Then the next, you calculate the variance covariance matrix for the standardized data, and then you get the eigenvectors and eigenvalues of the variance covariance matrix, and then you sort and graph your eigenvectors and eigenvalues pair. So with this process here, let's go ahead and begin. So let's go ahead and import pandas as PD. I don't think I'm gonna use pandas, but I still want to go ahead and import it. Import numpy as np from sklearn preprocessing. So let's go ahead and create dummy data for our PCA. And also from here, I'm gonna do from numpy import array. Alright, so I'm just gonna do X. As you can see, we just created some dummy data that we are going to be working with. It's a numpy array. So the next step is to standardize our data. So first we instantiate our standard scalar, and then we are going to fit the scalar to the data. So we're just gonna call this z is equal to, let's call it scalar dot fit transform, and we want to fit transform our x value, and let's go ahead and do z here. As you can see, this is our new data set after it has been fit transformed after like the mean has been subtracted from each one of these values, and each one of these values has been divided by the standard deviation. So the mean is 0 and the standard deviation is 1. That's the standardization process. So the next step here says to calculate the variance covariance matrix, and if you're doing this manually, you have to do this first before you get to this. But since we are using Scikit-learn PCA library, it will automatically calculate the variance covariance matrix and then apply the erg decomposition to this variance covariance matrix. So we don't have to do this manually if you are using Scikit-learn library. So with that being said, the next step is to instantiate our PCA. So we'll just call it PCA is equal to PCA, and here in parentheses we can put something like 4. Okay, so basically this 4 is number of components to keep. So basically what you're doing right here, you're saying like how many components do you want to keep? Do you want to keep 1 component, 2, 3, 4, 5? Or if you don't pass in any number right here, all the components is gonna be kept. So let's just do it first without passing in any number here, and then we'll come back and do it again and pass in something like 2, 3, or 4. Now let's fit PCA on the data. So here we just do PCA.fit, and then in parentheses we pass in z. So now that we have fit this PCA on our standardized data, the next step is to access the eigenvalues and the eigenvectors. So if you look at the documentation for Scikit-learn PCA and you scroll down here, you can see that it has attributes called component, explain variance, and the explain variance ratio, and other component. So these are the components that you have access to after running your PCA. After you fit your PCA through your data set, you have access to these values. So let's do eigenvectors. And our eigenvectors can be gotten by doing PCA.component. And these are our eigenvectors right here. And then we can get our eigenvalues, and we do PCA.explain variance. And this right here are our eigenvalues. As you can see, our eigenvectors are 2 vectors right here, and our eigenvalue are like the two values that scale these vectors. So this eigenvalue is, let's say, stretching our vector, and this eigenvalue is squishing our vector. Now what we are gonna do is we are going to transform our data. If you look at Scikit-learn here and scroll down all the way down to methods, you see that it has a fit method, and then it also has a transform method. So the transform method is where you apply dimensionality reduction to our data. This is our data. When we do PCA dot transform, is going to do dimensionality reduction on our data right here. You could do this in a single step. Okay, you could have done fit transform, which is fit the PCA model to our data, and then transform it at the same time using this code. But I did it individually, and it's fine too. So now we are going to call it, I don't know, something like A is equal to PCA dot transform, and we want to transform X. And let's just type in A here just to see our result. And this is it. This is what our transformed data looks like. So this is basically our PCA using all the pieces, all the principal components. Let's say we only want to keep a few principal components. So here we'll type in something like 3, and let's go and run this. Oh, actually, so if you pass in 3 here, it's gonna throw an error. Okay, so our pieces has to be between the minimum of 0, has to be between 0 and the minimum n samples n futures, which is equal to 2. So in this example that we have here, we only have 2 futures. Okay, so we can't have 3 as our principal component. If you have, like, let's say 10 futures, I think you can have between 0 and 10 PC. So you can pass in 10 here. So in this situation, I'm gonna do 2, and let's run this again. Now it's no longer throwing an error, and we can go ahead and run this. The answers doesn't change much. So our answer doesn't change much, almost everything stays the same, but I just wanted to show you that you could pass in a value here to determine how many pieces to keep. So this is our X values and Y values. If you remember earlier, I put our X to be a bunch of numbers 1, 2, 3, 4, 5, 6, 7, 8, all the way to 12. And then so this 1, 3, 5, 7, 9, 11 is our X values, and 2, 4, 6, 8, 10, 12 is our Y values. And of course, I'm using all of this as an example. So now we are going to plot our data frame before using PCA, and then we are gonna plot it again after using PCA. So here we are just gonna do df is equal to pd.dataframe. That's pandas. I told you to come in handy. And we're just gonna create a dictionary, and then we're gonna say our X is gonna be X values, and then we are gonna do Y is gonna be Y values. All right. And let's just do df.head just to get a preview of what data looks like. So our data set, our data frame is basically this exact same thing here, or this exact same thing, but in a data frame format. So now let's go ahead and plot it. So I'll go ahead and import matplotlib. Yep, go ahead and import that. And then we are gonna do plt.scatter. And we want to do a scatter plot between our X values and our y value. And let's do PLT.title. And we want to see before PCA and PLT.show. So right there, this is our data before doing principal component analysis. Okay. So now what does our data look like with principal component analysis? So I don't know if I made it clear before. These right here are actually our principal component. I mean, I named it A. Should I just call it pieces to make it easier? Pieces. And let's go ahead and run this again. It's the exact same information, but these are actually our principal component. So we are going to graph this principal component and kind of compare it to our before PCA graph. So if we do pieces like I named it and do this indexing technique, comma 0, as you can see, it just gives us the first set of values. If we go ahead and do pieces here, as you can see right here, -2, -4, -7, those are all these values right here. So this indexing technique basically says give me the rows and the columns, and then give me everything located on index 1. All right, and then if I go ahead and copy this, and let's say do 1, it's gonna give me everything that is right here on the second column. But if I do 2, it's gonna do index out of range because we don't have that here. So if I do 2, it's gonna do index out of range. Okay, so if I'm gonna be using this right now, and I want to make sure you know where it's coming from. All right. So this is our first principal component. Okay, so with that being said, let's go ahead and visualize PCA results. So we're just gonna do PC1 is equal to PCS. PC2 is equal to, and I spelled that wrong. It's equal to PC1. And we already have matplotlib. Let's go ahead and do plt.scatter. We want to do a scatter plot between PC1 and PC2. And plt.show. And I spelled something wrong again. And also let's go ahead and add plt.title. And let's see data after PCA. All right, so basically after doing principal component analysis, this is what our data looks like. And this is what our data looks like before doing principal component analysis. And this is what our data looks like after doing principal component analysis. So real quick before I end this video, I just noticed that I made a mistake. Right here when I did PCA.fate transform, I did fate transform X when I should have done fate transform Z. So if you remember correctly, Z is our scaled data. Right here I did scalar.fate transform X, right? So Z is our scaled data, and when I did the fate, I fit the PCA on our Z data, and here I'm supposed to do the transformation on the Z data too, not the X data. All right, so I just fixed it. So here it shouldn't be X. So you transforming our scaled data just make this more obvious. So I just noticed this mistake right here, and then everything here basically stays the same. You can go ahead and plot this, and this is our data before PCA, and then these are our pieces like we saw above. And then if we scroll down here and we can visualize it, we can see what our graph looks like after PCA. So this is a more accurate representation of PCA. Yeah, just notice that mistake. And also, I'm just looking at this after graph of this after graph of PCA. It doesn't like look very nice, right? I just created this for the sole purpose of demonstration. That's why I created this dummy data. But now I am going to show you a nicer looking PCA using a more robust graph. So if I go down here and run this is just me pre-processing some data. And then if I go ahead and run this and then come back here and run this, you can see what our PCA look like. So this is an example of what PCA could potentially look like after you have done it on a real data set. So if I go ahead and do nat.head here, you can see that this is a really large data set with over 99 columns. And basically our PCA took those data set and brought it down to this cluster of columns. So it reduced the dimensions from 99 columns to only 15 columns. So when I did this, actually 10 columns in this case. When I did this, I said I wanted 10 pieces right here, but when I did the graph, I only plotted 2 of them. And I could change this to 2. And let's run this graph again. As you can see, our bubble looks a lot different. I could change this to 3. And as you can see, our bubble looks a lot different. And if I go ahead here and do PCA dot components, this is what our components looks like. Actually, I called it not PCA. Not PCA. So this is the component for this particular data set. And as you can see, it's huge. And then we can look at the not PCA dot explain variance. And this is the explain variance from this one. And then we can also look at the PCs themselves. So I called it not PC. So this is the principal component from this particular data frame. And if I go ahead and do something like this right here, you can see that this is the principal component, the third principal component, like the fourth principal component, because this is 3 and we're doing zero-based indexing. So basically in this situation I have 10 principal components, so I can do all the way to 9. If I do 10 here, it's going to throw an error, index out of range. So yeah, quickly before I ended this video, I wanted to show you that I made a mistake up here. I did transformation on my X data earlier instead of my Z data, and this is what the updated PCA looks like. And this is like using dummy data, but if you're using actual data, this is an example of what PCA can do for you. And this is how it reduces like 99 columns into just 10 columns in this situation, because we chose 10 pieces right here. And this is a graph of 2 of those pieces. Thank you for watching. Please give this video a thumbs up and subscribe if you like it. If you didn't like it, give it a double thumbs down and still subscribe. And also in the next video, I'm going to show you how to use a Sklearn to kind of help you explain your PCAs. And then I'm going to show you how to do PCA manually in the next video. And to get access to this notebook that I use in today's video, just go to machinelearningeducation.com. This is a platform I created just for you. And if you are here, you click on free data science resources and it will take you to this page. This is where I keep all my data science tutorial Python notebooks, including this one. I create a lot of YouTube videos and blogs, and I just find it easy and straightforward to take all that content and put it on the one platform. So that's machinelearningeducation.com/free. And you can also find me online at evidencen.com. This is my primary website where I have my data science blogs. And as time goes by, I'll add more stuff to my data science blog posts. And once you are here, you can also click on free data science resources and you'll also be able to get to this page. That's it for this video. If you like it, please give it a thumbs up and subscribe to the channel. If you made it this far in this video but you didn't like it, please give it a double thumbs down and still subscribe to the channel. Thank you for watching, and I'll talk to you on the next one. Bye.